this is what an integral is. So we're going to go back to finding the area under a curve, but there was nothing special about the curve y equals x squared. It's just the one we chose as an example. We want to be able to find the area under any curve on any interval. So we want to be able to find the area of any curvy shape. So we talk about it as areas under curves, which you've already seen has more significance than just an area. Okay, so there's our generic curve on a generic interval from A to B, right? So just picture it, it's not shaded, but just picture everything between A and B, and then sitting under the orange curvy thing, we want to find the area of that shape. So we're just doing the same process, we're just doing it generically, not on a specific thing. So we're going to take A to B, and we're going to chop it up into n subintervals. So not 4 or 8 or 1,000 or whatever, just n. It could be any. The way the picture is, it looks like 4, but just picture it could be anything. So they're all equally wide. So we chop it up. The width we're just going to call delta x. So remember what delta means change in. So however wide, however much x moved in that little interval, that's the width. So we're going to call that delta x. And those are all going to be the same. It's the heights that are going to vary. And then here's the kind of weird part. So x1 there can be any point in that first interval. So we saw it with left endpoints, and we saw it using right endpoints, and we kind of saw it using the exact midpoint. To really define this thing, we have to just make it generic, because it doesn't matter. As you know what we're going to do, n's going to go to infinity. So as n does that, it doesn't matter how you draw the rectangles. It doesn't matter which point in there you use. You can use the left endpoint to draw the height of it, the right endpoint, the exact midpoint, or any other point in between. So that's why we're saying, so x1 is just a generic point in the first subinterval. x2 is just some other generic point in the second subinterval, right? xi is any generic, what we call sample point in the ith subinterval. And if you look at those dotted lines, those are the numbers. That's the sample point we're using to determine the height of our approximating rectangles. So no matter what f is, the height of the ith rectangle is whatever f of that sample point is. So just look at the first rectangle. The height of that rectangle is whatever f of x1 is. That's where we draw the top of the rectangle. The height of that second rectangle is whatever f of x2 is. The area of a rectangle is height times width. So if the height is f of x whatever, that sample point, the width is always the same. So the widths are all the same. So the widths are all delta x. So like the area of that first rectangle is delta x, whatever that width is, times whatever f of x1 is. Wherever the curve stops there, that's how we've drawn our rectangle. Okay, I know this is a little mathy, but now we have a generic expression for the area of our ith rectangle, and now we get to add them all together, all the areas. And now we have to remember how summation notation works. So I know you've seen this before, that's sigma. This is called, well, it's called sigma notation or summation notation. Just very briefly, what it means is, okay, you start with I equals 1, and you plug that in for I. So the area of the first rectangle is f of x1 times delta x, height times width. And then you add, that's why it's called summation notation. Then you go up to I equals 2 and you add, okay, when you plug 2 into that thing, that's f of x2 times delta x, so that's the area of the second rectangle. Then you go up to I equals 3, I equals 4. You're adding all these terms together, all these areas, and then the n on top means you stop. So we had n rectangles, right? So the nth rectangle is just the last rectangle. So if we did 100 rectangles in there, n would be 100, and that would just mean you stop. That's just the last rectangle whose area you have to add. So if that looks unfamiliar to you, I'm going to need you to go back and review summation notation. This sum, this is a very important concept. It's called a Riemann sum, One of the fathers of calculus is a German guy named Bernard Riemann, so it's named for him. This idea was known by people like Newton in those days, but none of this stuff really got really codified and quantified and like proven until like the 19th century. Guys like Riemann and some other guys, whatever. So that sum, that approximation, right? That's not the area. That's just the sum of the areas of n rectangles. Has a name. It's called a Riemann sum, but it's not the area. You know what the area is. The area is the limit of that sum as n goes to infinity. So this is important. So you can think about it as we're adding way more rectangles, or you can think about it as our rectangles are getting skinnier. So as n approaches infinity, delta x goes to 0. Now, delta x can never be 0, just like n can never be infinity. We can't draw infinity rectangles. But we can look at a limit. We can look at the limit of what happens to that sum as n approaches infinity. So there it is generically. The actual exact area under that curve is the limit as n goes to infinity of that sum. So I know that looks like a lot of stuff, but just visualize it. Visualize what happens as we add more and more and more and more rectangles. They get much skinnier, and then the sum of those areas looks more and more like the exact area under the curve. If the rectangles did really have no width, they would just look like lines. So if you just drew a bunch of lines from the curve to the x-axis, right, that would essentially be like shading the area under the curve. So if you could somehow do that, this expression, this limit, would give you the exact area under that curve. The area we're talking about has a name. It's called the definite integral of the function from a to b. So on that interval. You can just call it the integral for now, because I haven't said what an indefinite integral is. I'm just being specific because that comes later. So rather than writing all that stuff, writing the limit as n goes to infinity of the sum from I equals 1 up to n of f of x sub I times delta x, we just write it with this thing. So you've certainly seen that thing, that long s. It is a long s for the whatever the Latin word for sum is. And the bottom number is what's called the lower limit of the integral, a. The top number is what's called the upper limit of the integral, b. So it goes from a to b. I'll show you a picture in a second. And then f of x just specifies which function you're talking about. The dx, I'll explain in a second. So that's the picture. So that big, weird, mathy looking thing, the s from a to b of f of x dx is just an area, right? It's just an area. And it's a number. It looks like a function, right? Kind of, because it's got a bunch of x's and stuff in it. But it's a specific number. It's a finite number, right? You can't have an infinite area. But for now, it's just a finite number. It's just whatever that shaded area is. We saw it before where it was 1/3. So think of the dx and the integral sign, the s, as being a part of the same thing. They're the same thing. The f of x just like lives inside of it. So you can think of dx as meaning what it always meant, which is with respect to x. So it's just specifying that x is the variable and not some other thing like t or whatever. Okay. If there were more than one variable in this thing, which you'll get to in multivariable calculus, that dx or dy or dz thing specifies which one you're doing the integral, like with respect to which variable. But it is essentially, it doesn't have a lot more meaning for now, but we will use it later in this class very soon. So I'm just going to say don't forget it. So just think of it as a part of the integral. The s thing and the dx are the integral. The f of x that sits in the middle of them is just specifying, oh, that's the curve we're talking about. So I'm just going to ask that you just don't forget about it. It's not extraneous. It's not just a thing that only math teachers write and care about. We're actually going to do math with it because we have to do something called substitution where we kind of change the variables. So I know it's weird notation. It looks like there's too much stuff there, but that's just what it is, and you'll be fine. There's the one concrete example we've seen. So it's just notation. Rather than saying, okay, the area under the curve x squared between 0 and 1 is 1/3. That's a lot of words. I can now just write that. The integral from 0 to 1 of x squared with respect to the variable x is exactly 1/3. And all that refers to is an area, right? That just refers to the area we saw before under that little parabolic curve. It's just a new way to write that. Rather than writing down all those words, the area from 0 to 1 of blah, 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 you just write this new thing. So get used to seeing that S symbol. Notice the computer sometimes writes the 0 and the 1 like by near the S instead of at the top and the bottom. It doesn't really matter as long as it's clear what's what. So the S is called the integral sign. The 0 and the 1 are called the upper and lower limits of the integral, or the upper and lower limits of integration. Integration is the art of doing these integrals, just like differentiating is the art of doing derivatives, or not the art, the act of it, I guess. And then again, it's a number. So that's what a definite integral is. It's just a number. It's just some number like 5 or pi. Whereas we have an indefinite integral is something that comes later, and that is a function. We have some kind of intuitive ways that these things work that we don't really have to prove. They just kind of make sense because of geometry. This first one is really the only one I'm going to get into because it's very important. So if you look at the curve pictured, some of it sits below the x-axis and some of it sits above the x-axis. Now, if you think, so look at that negative stuff. If you think about a rectangle in there, it's an upside down rectangle. And the way we defined this is that the height of the rectangle is the value of the function there. Well, the height of the rectangle is now negative. So I'm using the word height very loosely because heights can't really be negative, just like area can't really be negative. But this is math. We had to define this in a very specific way to talk about it, and we defined it as the limit of the sums of the areas of a bunch of rectangles. So technically in that negative space, that orange space, the width is always positive, the height of a rectangle will be negative, so the area will be negative. So that's negative area, right? And now again, technically area can't be negative, but now it can be, so shut up. Okay, so think about it as the negative area will cancel out some of the positive area, right? So the stuff above there, the green stuff, will be counted as positive area. The stuff below there, the orange stuff, will be counted as negative area. So you can think of an integral, if it really throws you off to think of like area being able to be positive or negative, think of an integral as like the net area. So the negative stuff will take away from the positive stuff. For example, you can do right now this integral. The integral from 0 to 2 pi of sine of x. So that's that graph. So we want all the area under that curve between 0 and 2 pi. And again, now I'm saying under the curve, but if the curve is below the x-axis, it's actually above the curve. So by under the curve, just think we always mean between the curve and the x-axis. If the curve's below there, we still mean between the curve and the x-axis. So technically we say above the curve. But that now we have this integral notation, we don't really need to say any of that stuff. You know what I'm saying, because that's what that math means. So just think about it. Think about the area from 0 to 2 pi there. Well, there's however much, you don't know, between 0 and pi. And then there's however much between pi and 2 pi. But if you look at those two shapes, it's the same, right? There's exactly as much area between 0 and pi as there is between pi and 2 pi. However, the area between pi and 2 pi is negative. So the actual net area between 0 and 2 pi is 0, right? You don't need to really do any calculus to see that. You just say that, oh, this is a very symmetrical looking shape, so the stuff up here is canceled out entirely by the stuff down here. Right, so without doing any calculus, that total area is 0. And that's why I keep putting area in finger quotes, because area is something. It's not really 0. So that's just a quirk of the way we defined it. We've got these upside down rectangles with negative heights. Obviously, if we just really wanted to know what that actual area was, you just take the first part and just multiply by 2, because it's the same. Or you just take the second part and, okay, that area does turn out to be 1. Instead of having it be negative, just flip it to being positive. Just take the absolute value, right? You can just chop it up and take absolute values. So if this were an actual geometry problem, like this wouldn't really be a problem for us. It's just you'll see that when you do the math and you actually do the integral, like the way we're going to do it, you would get 0 for that answer, and that's why. This is one of those parts where I'm going to just ask you to do some reading. So it's boring for me to go through all the properties. So look in section 4.2 on just properties of integrals, and just look over the rules and just do the homework. I mean, if you just do the homework from this chapter, I'll make you use this stuff. So they're exactly kind of like a lot of the rules for derivatives and for limits. In other words, the integral of a constant times a function is the constant times the integral. So constants come along for the ride, right? That rings a bell. That's the same as with derivatives. The integral of the sum of two functions is the sum of the two integrals. So in other words, if you had like a polynomial like x squared plus 2x plus 1, you can just do those three functions all separately and just add that stuff together. And the book is nice because if you look just visually rather than prove these properties, you can kind of see visually why that would work. When you take a curve and you multiply it by 5 or whatever, that's just called a vertical stretch. So it just stretches the whole function up by a factor of 5, which just means you have 5 times as much area under that curve as you did before. So you can just see geometrically why that would work like that, and we don't need to prove it. We could, but I'd rather you just go over them. And just think of it as cases where math works the way you want it to work. Unlike with something like the product rule, where math actually does some other thing and there's some rules you now have to memorize. These are just intuitive cases where the simple thing that you think should happen does just happen to happen. So we will reference and use these rules going forward, but they're easy.